Hello everyone, I'm Wang Qian from Institution of Automation, Chinese Academy of Sciences. I feel great honored to share my work on touch-based interactive machine translation. My presentation will be in 5 parts. First, let's look at the task of interactive neural machine translation. A standard machine translation system translates a given source sentence into a target sentence without human interaction. However, fully automatic machine translation systems are still far from perfect in many cases. Many human-machine interaction approaches have been proposed for allowing human translators to involve in machine translation process to improve the final translation results. In the research area of IMT, researchers focus on interaction, which aims to both reduce human effort and improve translation quality. Next, let's look at some IMT methods related to our work. Researchers have introduced different levels of human-machine interaction. Due to the left-to-right decoding order of machine translation, the most intuitive method is prefix constraint decoding. In this kind of works, a human translator validates the translation results and corrects the first error. The underlying model takes the left part as validated prefix and redecoding the remaining of the right part. The prefix-based protocol is inflexible since the users have to follow the left-to-right order. Another line of works focuses on interaction at arbitrary position. In these works, human translator directly modify crucial errors in translation results. The model is then asked to redecoding and force the lexical constraints like words or phrases to appear in the final translation. Recently, some researchers resort to more flexible interactions by incorporating multimodal interactions. Instead of traditional keyboard input, the multimodal methods allows human translators to interact with mouse, handwriting, speech, or finger touch. These methods enhance the user experience and meanwhile reduce the human effort for obtaining final high-quality translation. However, these interaction methods is not convenient for mobile devices, which provide a variety of touch actions. Also, these methods do not make full use of the power of deep neural networks. Therefore, we pay attention to different kinds of touch actions on mobile devices and use the neural network to predict refined translation based on these actions. We first define the touch actions provided in our interaction method. The action should not only follow human edit operations, but also be intuitive with touch screens on mobile devices. As shown in the example, given a source sentence, the translation model will generate an original hypothesis, which may be different with reference. If a user wants to modify the hypothesis into reference, 4 edit operations can be adopted, which are insertion, deletion, substitution, and reordering. There also exist at least 4 kinds of gestures on mobile devices, like tap, swipe, long press, and drag. Therefore, we define 4 kinds of non-lexical actions, which we call touch actions. The insertion action means that a new word should be inserted into a given position. The deletion action means that a word at a given position should be deleted. The substitution action means that a word should be substituted by another word, and the reordering action means that a segment of words should be moved to another position. Note that these actions are non-lexical. For example, for the substitution action, it allows the user to only indicate which words should be substituted. With the non-lexical attribute, our interaction method can be flexibly performed on mobile devices. Since we have the original hypothesis and corresponding actions, the goal of our model is to generate refined translation. We first apply the touch actions on hypothesis to obtain a modified hypothesis my prime and an action sequence A. The modified hypothesis, as shown in the example, is modified from the original hypothesis y prime by reordering the segment in gray color with the reordering action, and inserting a special token INS with the insertion action. The action sequence A includes S for substitution, I for insertion, and D for deletion. Now we have the source sentence X, the modified hypothesis my prime, and the action sequence A as the model input. We design a dual encoder model to generate refined translations. The model includes a transformer encoder and a transformer decoder, as in standard transformer-based models. To incorporate with MYPRIM, we add another encoder into the model, which we called hypothesis encoder. Different from transformer encoder, the hypothesis encoder uses an actions positional embedding instead of fixed positional embedding. The action positional embedding includes 4 embedding matrices, a non-action embedding, and 3 actional positional embedding for insertion, substitution, and deletion. For the S word in a sentence, the model first chooses the corresponding position embedding matrix based on the S action, and takes the S row of the matrix as positional embedding of the word. In decoding, the actions we defined can be provided by human translators in real applications. However, it's impractical to manually collect a large-scale dataset for training our model. Thus, we propose an automatic data annotation method to extract editing actions from a machine translation hypothesis and its corresponding reference. We first train a neural machine translation model and translate the source set of the entire dataset. Then, we follow the algorithm of TER to calculate the number of edit operations required to transform the hypothesis into reference, and record the actions to obtain modified hypothesis MYPRIM and the action sequence A. We use the automatically annotated data to conduct a simulated experiment. We conduct our experiments on 3 public datasets with different sizes into 1 small IWSLT dataset and 2 WMT datasets. The data statistics are shown in the table. For the baselines, we compare our method with automatic machine translation methods and the interactive machine translation methods. The 2 automatic NMT baselines are CNN-based model and transformer model. The IMT baselines include quick edit, which allows the user to mark incorrect words in original hypothesis and regenerate translations. It can be treated as a combination of deletion and substitution actions in our method. The original quick edit method is built on CNN-based model, and we implement quick edit with the transformer model. The touch baseline directly performs reordering and deletion actions on original hypothesis without regeneration. We use BLEU and TER as metrics to compare different methods. The main results are shown in the table. It's obvious that with more interaction actions, our method strongly outperforms automatic machine translation and quick edit. Comparing to touch baseline, our method also achieves extreme higher performance, which shows that the lexical prediction of insertion and substitution actions are crucial for translation refinement. We also notice that the improvement is higher with a large dataset. The reason may be that the underlying NMT model is overfitting on the small training dataset, and thus the hypothesis of training data requires less edit, on which we build our simulated training dataset. To further investigate model capacity, we conduct 3 experiments on WMT English to German dataset. We first evaluate the word reordering quality of our method. We adopt 2 evaluation metrics. The one is to use TER to calculate the number of words that should be reordered. The other is RABIX, which is based on rank correlation. As shown in the upper left table, our method performs better with reordering actions than vanilla NMT and IMT baselines. Due to the non-lexical nature of touch actions, the model must predict the correct words to insert or substitute it. For deletion actions, we do not explicitly remove the words that marked as deletion, and the model is responsible for making decision whether the words should be deleted. We evaluate the accuracy of the 3 actions. As shown in the lower left table, the deletion accuracy indicates that the model can remove over-translated words. The higher insertion and substitution accuracy can be attributed to disambiguation ability of self-attention model. We also investigate the influence of different actions by providing different kinds and different number of actions. This also confirms the scenario in partial feedback in real applications. From the right figure, we can find that the translation quality is highly correlated with the percentage of actions provided. Meanwhile, the substitution actions and the reordering actions is more important than the other two actions. So far, our experiment is conducted on simulated dataset. However, in real applications, our method faces three major challenges. The first is action inconsistency. In training data, the translation hypothesis and reference are individually generated. In real applications, the reference is modified from the initial translation, and thus the extracted actions may be different from human-provided actions. The second is data inconsistency. There may exist a domain mismatch between training and inference. The last is model inconsistency. In previous experiment, the initial translation is generated by a transformer-based NMT system. However, the underlying translation model may vary from phrase-based SMT to most advanced NMT system. We use dataset from WMT APE task to further evaluate our model. The post-editing dataset from IT domain is generated by a PBSMT system. The result shown in the table indicates that our RMT method is more robust when facing the three major inconsistencies. We also conduct a free-use study to evaluate the usability of our method. The interview shows that the touch editing is intuitive and flexible on mobile devices. However, it sometimes cannot generate final high-quality translations and requires further post-editing. It can be treated as a lightweight proofreading method and suitable for pre-post editing. Finally, let's conclude our work. In this paper, we propose a flexible and effective touch-based interaction machine translation approach, which allows human translators to revise machine translation results through touch actions. We present a simulated action extraction method for constructing training data and a dual encoder model to handle the actions to generate refined translations. For the future works, we plan to improve the word selection accuracy with non-lexical actions and conduct large-scale human evaluation to evaluate the productivity of different IMT methods. Thanks.